Abhijit Gadde with us today, and he will talk about modularity of supersymmetric partition functions. Go on, Abhijit.
Thank you very
much. And as usual, please feel free to ask questions. Just unmute yourself and ask whenever you want.
Or in the chat.
Or in the chat.
Yes, yes, please certainly do. Thank you very much, Shlomo, for inviting me to give the talk. I'll talk about certain modular properties that partition function of supersymmetric theories in 4 dimensions enjoys. The ideas that I will talk about are quite general, and this program, it seems, can be generalized in multiple directions, including even non-supersymmetric theories. But I will, for concreteness, I will focus mostly on the 4-dimensional n equals 1 theories. Now, one is certainly familiar with modular properties of 2-dimensional conform field theories on a torus. And this is because of the large diffeomorphism group SL2Z of the torus. And among many applications of modular invariance, one of the most celebrated one is, of course, the Cardy formula, which tells us the density of operators at high energies in terms of its central charge of the theory in a universal way. Now, apart from the Cardy formula, the modular bootstrap recently has been effective in imposing bounds on the gap between the first excited state and the vacuum as well. So, all in all, the invariance of the partition function under the large diffeomorphism group of the torus has been quite powerful. Now, we know that conform field theories in higher dimensions obey constraints of unitarity and crossing. This forms the basis of what we know as conformal bootstrap, and this has been very effective in putting various bounds and constraining the space of CFTs in a dramatic way. But a natural question one can ask is, are there any other constraints apart from these, which are similar to the modular invariance, the constraints of modular invariance in 2 dimensions? Now, if one were to have a partition function which is invariant under some sort of a modular transformation, as in 2 dimensions, one would expect this invariance to come from the large diffeomorphism group of the manifold on which you are defining the theory or on which you are computing the partition function. So a natural choice for such manifold would be a D torus. It has a very big large diffeomorphism group, which is SLDZ. But of course, one could choose to study partition function on this space, but it does not let us do what we want to do, namely to constrain the spectrum of local operators. Because as you know, it is in 1-to-1 correspondence with the Hilbert space on SD-1. So the partition function that we really want to constrain is the one on S1 times SD-1. In D equals to 2, this is the familiar torus, and it has the non-trivial, a very big large diffeomorphism group. But in 3 dimensions, this space S1 times S2 does not have a very big large diffeomorphism group. This group in D equals 3 is simply Z2 times Z2. And one can understand this as an antipodal map, a composition of antipodal map on S1 and the antipodal map on S2 for one Z2. And the other Z2 comes from the non-simply connected nature of the diffeomorphism group of S2. It turns out that the diffeomorphism group of S2 homotopically is identical to SO3. And as you know, pi 1 of that is Z2. So as you go around S1, you could go and make a circle in that large, in the diffeomorphism group S2, which will give you the other Z2. This is perhaps true also for D equals 4, that is when you consider S3. Now, these groups are quite small compared to the 2-dimensional case, so they are not very constraining. In higher dimensions, almost nothing is known about the large diffeomorphism group of this manifold, but it is perhaps safe to assume that it's not going to be as big as SL2Z. In particular, to probably be a finite group. So this seems to lead to a pessimistic conclusion that the partition function that we want to constrain doesn't quite have any hope of being modular invariant. But there is a hope, and this comes from the following observation. There is a special mathematical function called elliptic gamma function. It's a function of 3 variables, which I'm calling Z tau, and sigma, and it enjoys this property, where the product of three gamma functions with these permitted arguments gives you a phase, a pure phase, which is explicitly written like so. Now, it just so happens that this function is the superconformal index of the chiral multiplet of R char 0. Now, from that point of view, for the Z, so the superconform index, as you know, is the supersymmetric partition function on S3 times S1. So what are these parameters then? The Z is the background holonomy for the U1 symmetry under which this chiral multiplet transforms. Tau and sigma are the parameters that describe how S3 rotates as it goes around S1, or you could also think of it as a complex structure, complex structure parameters of complex structure modular of this S3 times S1 space. As it turns out, this property can be understood as a sort of covariance under the group SL3Z. And SL3Z is a large diffeomorphism group of 3 torus T3. So where is this property coming from? In particular, where is this T3? So this is what we will try to understand in this talk. And that understanding will let us generalize this property to not just chiral multiplet, but to other theories as well. But before we do that and move to 4 dimensions, let us first review modular properties of supersymmetric partition function 2 dimensions. For concreteness, I will talk about 2,2 theories. So the partition function question is on the torus. It's known as the elliptic genus. I'm defining it to be the trace -1 to the f in the RR sector so that it enjoys the invariance under full SL2Z. And this is a function of 2 variables, Z and tau. Z couples to the left moving R symmetry, tau couples to the left moving conformal dimension. Geometrically speaking, tau is the complex structure of the torus and Z is the background holonomy for the left moving R symmetry. Now, if the theory were to have other global symmetries, one could turn on holonomies for their Cartan generators as well. So if the global symmetry has rank R, this would be a function of additional R variables. Now, so far we were talking about large diffeomorphism group, the invariance under large diffeomorphism group of a partition function, but it pays off to think of large gauge transformations on the same footing as well. And in this particular case, they will be generated by shift of Z by 1 and by tau. This would be the large gauge transformation around one cycle of the torus and the other cycle of the torus. And this generates the Z squared. So altogether, the group of large symmetries is SL2Z semi-direct product Z squared. It's a semi-direct product because clearly SL2Z acts on this Z square, on this shift, the group of shifts. If you were to have more variables corresponding to Cartans of the global symmetry, then you would have additional factors of Z squared corresponding to each Cartan. Explicitly speaking, the action of this group element on these parameters is given here. If G1 is an element that belongs to this, it acts on Z and tau in this way. G2 would act on Z and tau in this way. It just acts on Z by shifts, as I said. Now, the modular property of the partition function is succinctly stated in the following way, that the partition function evaluated on the background with these parameters and the partition function evaluated on the background with these parameters, which are related to these by just an action of G, which is the element of the large transformation group, is almost equal, but except up to a phase factor which appears like so. Now, you could understand this geometrically, this phase factor, by considering a 3-dimensional space wherein it's a mapping cylinder which connects a background with these parameters to a background with this parameter, and there is a 3-dimensional space in between them. And if you were to evaluate anomaly Chern-Simons 3 form of the theory in this space, you would produce this particular phase. And another sign that this is related to anomalies is that by redefining these partition functions, you cannot get rid of this phase. Now, just from this equation, you can see that these phases must obey an equation of this sort. Okay, and geometrically, you can understand this by concatenating two cylinders of this type. So going from this to G, and then G1 and G1 to G2, and thinking of it as a direct a big cylinder. So this would give you this particular equation. And as I said, because this coming from the anomaly, you cannot get rid of it by introducing local counterterms, or in other words, redefining the partition function z to some z prime. Now, but what we can do is to set, so I should mention that because these phases obey equation of this sort, if we know this for generators of the SL to Z times Z squared, then we can compute this for any other group element, because this would be computed by this formula. So you can choose your counterterms in a way that all the phi g's corresponding to all the generators, the phi g's corresponding to all the generators are 0 except for 2 generators. And one can choose those generators to be the S transformation and the shift by tau. And for a theory, for a 2,2 theory with central charge C, these phases are the following, are the ones that are written in the formula. Now, the meromorphic function that transforms in this particular way in mathematical literature is known as Jacobi form of weight 0 and index C over 6. And it's a classic topic of study in mathematics to classify the space of such Jacobi forms. And I think a lot is known about the space when the index is taken to be an integer. Now, if you had other variables, other global symmetries, then the form of these phases would be more general and will encode the 't Hooft anomaly of the theory. And also for a slightly less supersymmetric case, namely the case of 0,2 supersymmetric theories, you would obtain a more general form of these phases. Nevertheless, you could compute these in this mapping cylinder way that I mentioned. Now, given that we have this equation that the partition function must satisfy, one can take the following point of view. If the partition function is taken to be a good stand-in for the theory itself, then this equation, using this equation, one can try to ask a question, which is, let's say a theory has a certain anomaly polynomial, which will fix this set of phases. Then what is the space of theories with that particular anomaly polynomial? And that will boil down to solving an equation of this kind, or parameterizing the space of solutions to this equation of this kind, or this equation itself. So in this way, you can think of the modular transformation properties of the elliptic genus as a kind of a bootstrap program for theories with a given anomaly polynomial, two-dimensional 0,2 theories with a given anomaly polynomial. Okay, so again, before we go to 4 dimensions, let us formalize this discussion a little bit more and develop some words which will let us talk about 4-dimensional cases as well. So let me talk about, let me call the space of meromorphic functions of Z and tau, or more generally, these, if you have other parameters Zi's and tau, to be n, and I will call the spaces of phases to be m. Okay, so these phases that I talked about, they belong to m, and the partition function itself is an element of n mod m, because I'm modding this out by m because I'm letting it have additional multiplicative phases. Yes.
Hi Abhijit, can I stop you for a question?
Yeah, please.
Can you go back one slide?
Yeah.
Sorry. Okay. So when you say that this is like a bootstrap program, are you sure that?
Yeah.
I mean, is there an argument? Maybe I missed it, or I don't know. Sorry for the naive question, but there is there an argument for which you expect that for every modular form of this kind, there is a 0,2 theory that has there is not, right? It's not.
Yeah, right.
So it's an over-parameterized space in a sense.
In a sense, yes. Yeah, I mean, it's
I mean,
not
the converse is true, right?
But what about 0,1?
Yeah, the converse
theory?
also, I'm not quite. Sorry.
What about
no,
0,1? Maybe then.
Well, 0,1 theory will not let you have this additional parameter z, which couples to the left moving R symmetry, because there's no R symmetry. Yeah, so in both directions, I think this is a bit of a stretch, that there may not correspond the theory to a solution of this equation. Also the other way around, I think, because there may be two theories which a priori
have the same index.
Identical index. Yeah, I mean, I don't have an argument to rule this picture also out. But nevertheless, it will give you some understanding about the space of theories.
Yes. Thank you.
Yeah, it's a good point. Thank you. Hello, Nandi, do you have a question?
Yeah, so you said that can you hear me?
Not very, you're not audible, you're not clearly audible.
I don't know. I don't know.
Sorry, is it just me?
No, I also cannot hear.
Nati, maybe you can type the question and we can read it.
Please type the question.
Can you hear me now? Does it help?
Better.
Yes, better.
Okay, I know. Wow, it was my fault. You had a comment about 2,0 theory, and you said that there are more options or less options.
More options for the phase.
Is there a clear way to see why it is so without getting into the nuts and bolts of what you're doing?
Well, I simply had in mind that 2,2 theories would be a subset of 0,2 theories in nothing deep.
But in what way does 2,2 restrict the possible anomaly?
Well, there are probably more constraints that you could get from the supersymmetry being 2,2 rather than 0,2. I mean, in particular, one could talk about C1, C left and C right to be different. In this particular, in the 2,2 case, they would be the same.
Thank you.
So that's just a particular point.
Thank you.
Which, yeah. Okay. So let's see. Yeah. Okay. So here I was talking about I was introducing some language here. So as I said, the phases then are elements of the space M, and the partition functions are the elements of the space N mod M. Now, I should say that one should not think of these N and M as just spaces of functions, but one should think of them as G modules. G modules, not very rigorously speaking, are spaces which also have a G action of some group on it. So, given that these N are the space of functions of these variables, and I already told you how G acts on these variables, that gives them an action of G. So which makes N and M G modules. Now the equation that is obeyed by the phases, which I wrote on an earlier slide, this is known as the first group co-cycle condition. Okay, this is the first group co-cycle condition. It's kind of like a co-cycle condition for forms, in which case, in this case, the index G denotes the number of G's that appear here denotes a kind of a degree of this form. So in that sense, it's a form that obeys the first co-cycle condition. I mean, one can actually make this analogy rigorous by going to the classifying space, etc. But let us not do that. So just intuitively, let's understand this as some sort of a co-cycle condition. Now, a trivial solution to this condition, of course, would be e to the I phi g is e to the I chi minus chi of g inverse. Okay, if you just put it in, things will cancel and you get this equality will be satisfied. But if this were the case, then you could absorb this chi in the definition of z, and then you would be able to get rid of this phi completely from the previous transformation equation, which we said is not possible. That means there is no solution of this kind for this e to the I phi g. So that makes e to the I phi g satisfy a co-cycle condition, but it's not simply a co-boundary. It's not simply an exact form. It's a closed form, but it's not an exact form, which makes e to the I phi g a non-trivial element of the group cohomology. Okay, I'm not going to define this rigorously, but in this very intuitive terms, that this is a co-cycle and this would be a co-boundary, one can understand e to the I phi g as an element of the group cohomology. And this is the first group cohomology because phi only has one G label. And this is the group that is appearing all over the place. And this M is the coefficient space in which it takes the values. So as I said, this phi belongs, e to the I phi belongs to M. So that's why I'm writing this statement like so. Now, because this is the case, you could also think of the partition function as the zeroth element, non-trivial element of the zeroth group cohomology, which takes values in n mod m. Okay. So now with this language, we can state the result that we have for 4 dimensions, and then the rest of the talk will be explanation of this result. It's just good to have it in front of us so that we know where we are going. That's why let me state it immediately. So in 4 dimensions, what we are going to do is we are going to define partition functions, supersymmetric partition functions, and the manifolds that we will be defining them on will be labeled by some group G, okay, or group element of some group G, which is SL3Z times Z cube to the power R. And so that's why the partition function is going to have a G label, okay, and it's going to be a function again in the same way that a 2-dimensional partition function did. It's going to be a function of a bunch of global symmetry, background global symmetry holonomies, and 2 geometric variables. These would be the complex structures, modular space, moduli of the geometry on which we are defining. So that's what makes us this object for us, this Z, G, tau. This vector tau is a collective notation for these variables, okay? And then the main result is that the partition function obeys the first group co-cycle condition, which is this. Now note that this is the condition that was obeyed by the phases in the 2-dimensional case, but in 4-dimensional case, it's the partition function itself that is obeying this condition, okay? But not quite. It fails by again a phase, but because this equation now has 2 G labels, this phase also going to have 2 G labels. And then just by virtue of this equation, this phase obeys the second group co-cycle condition, which is written here. This is nothing mysterious. You just take this.
Maybe I missed that. Is this something you're going to prove, or is this something you already argued for?
No, I'm going to prove.
And the second question is, are you going to explain why there is an SL3Z in the first place?
Yes, very much so. Very much so,
yeah. I thought I missed it.
No. So as I said, let's just first have this result in front of us so that we know where we are going. That's why I chose to present it in this way. So as I said, the partition function that will appear in our story, Z, is going to be a function of this bunch of variables and also going to have a label, a G label, which corresponds to a G-type geometry, which will become clear soon. And then that is going to obey this first group co-cycle condition up to a phase. And this phase itself is given by 2 group elements, G1 and G2, and that obeys the second group co-cycle condition. Okay, and because you cannot, just like in 2 dimensions, you cannot get rid of this phase by redefining this partition function. That means there is this phi G1 G2 does not admit a trivial co-boundary type solution, which makes this a non-trivial element of the second group cohomology, which is what I've written here. Okay, here this G is not SL2Z, but SL3Z times Z cubed to the power R.
Abhijit?
Yes.
There was a question in the chat. Is e to the a phase or an element of M?
Yeah, so M is what I'm calling phases, but if I were to be very precise, I should call this M space of nowhere vanishing entire functions. Because I'm not quite looking at the real slice. You know, phase only makes sense if I look at a real slice, but as a holomorphic statement, I should say M is the space of nowhere vanishing holomorphic functions. And that's what e to the I phi is, G1, G2. So that's why this M appears here. So the rest of the talk is going to be discussion of this slide, these results. I should say that here I was referring to this Z as the partition function, but they are going to be slightly different from partition functions, as will become clear soon. Yeah, here again I elaborate on this picture, but perhaps I can skip this slide, because if okay, let me just say this. So as you can see, what this equation is giving us are constraints that the G partition function must obey. Okay, that a partition function corresponding to G1 and the partition function corresponding to G2, they multiply to give you partition function on G1, G2, like so. Okay, so that means if you know these partition functions for generators of these groups, then you can compute the partition function for any other element of this group. So this would give you a way to compute partition functions for, you know, different geometries, but how is it going to give a constraint on the partition function itself? Well, that is easy, because that constraint simply comes because group generators also obey relations. So let me talk about a particular relation for a particular group element, which will play an important role. So in SL3Z, there is an element Y which cyclically permutes 3 entries. If you think of SL3Z as a 3 by 3 matrix acting on a 3-dimensional vector, then there is an element Y which cyclically permutes the entries, and hence obeys Y cube equals 1. Now this is the relation that a single generator must obey. So if you evaluate the cocycle condition on this relation, you get this. Now you see that the partition function that is appearing here is ZY. All the partition functions are ZYs, albeit evaluated at different parameters. And this equation precisely translates to the condition that is obeyed by the gamma function. Okay, so this is how we will understand from this cocycle condition this property that the gamma function obeys. Okay, so let me not elaborate on this further. This will become clear in due course. Okay, so now we'll get to the construction. So I will first start by explaining where this T3 is, under which under whose large diffeomorphisms these things obey these nice properties. So this T3 comes from thinking of S3 times S1 as being obtained by gluing 2 copies of solid 3 tori. Okay, so a more familiar gluing of this sort is perhaps if you forget the S1 that just goes around for the right, and if you just consider S3, now you know S3 can be obtained by gluing 2 solid tori, but where you glue a contractible cycle with a non-contractible cycle, and the non-contractible cycle with the contractible cycle, and this way you obtain S3. Alternatively, you can think of S3 as fibering T2 on an interval where one cycle, A cycle of T2 strings on one side and B cycle of T2 strings on the other side, and that gives you S3. And this S1 simply goes for the right. Okay, so in the end, we get a picture where we have one solid 3 torus on one side and the other solid 2 3 torus on the other side, but we don't glue them. We don't glue the contractible cycle with the contractible cycle, but we do the shuffling of this kind. So picture, this cartoon of this gluing is the first picture, in which I have also labeled the geometric parameters of this T3. So these parameters sigma and tau, you can think of them as describing how this circle fibers over this circle and how this circle fibers over this circle. But for simplicity, I have taken these torus to be a rectangular torus. So sigma and tau are simply lengths of these cycles, but you can make them complex by also allowing non-trivial vibrations along this circle. But for simplicity, let's just think of sigma and tau are just lengths of these circles. So you have one solid T3 here. By this, I mean this disk is contractible. And I do it this way and not just shade it here because I want to think of this as a cigar. And on the other side also, we have a similar picture, except that the contractible cycle has a length tau so that it can glue with the non-contractible cycle. And this one has a length sigma so that it can glue with this. And together, if you glue this, you obtain the geometry as 3 times S1. Okay, so this is a bit fast. You know, one has to do a particular type of partial topological twist so as to preserve supersymmetry and so on. But if you do it correctly, you will get S3 times S1, where the sigma and tau will be familiar parameters that appear in the superconformal index. Now, it is this solid T3 whose large diffeomorphisms are appearing everywhere. Because instead of choosing to glue with this particular element of SL3Z, I could choose to sandwich any large diffeomorphism element of this solid T3, which will let me obtain geometries which are labeled naturally by the group element G that I use to glue these two sides. And that geometry I'm calling MG, and the partition function on that geometry would be ZG. Now, so the kind of geometries that one obtains are essentially lens spaces, LPQ, and also S2 times T2, and this is a particular type of lens space. So these are the geometries that one is obtaining by allowing gluing by any group element G of SL3Z. And you know, Nati and friends had taught us that in order to preserve supersymmetry on this set of manifolds, R charges of these theories are required to be even integers. Now, we will assume that the theory contains an R symmetry with this property. You know, that R symmetry need not be a superconformal R symmetry, but if you can mix some global symmetry to the superconformal R symmetry to obtain R charges with this property, that also will be fine. So we'll assume in the rest of the talk that this is indeed possible. Okay, so now we know how to construct these manifolds MG and how to compute supersymmetric partition ZG on it. So these are the partition functions that I have in mind, but not quite, as you will see. Now the partition function ZG on this manifold MG, we can think of this as an inner product of this bra and the ket. But the bra is on this is defined for the torus with these parameters, while the ket is defined for the torus with these parameters. That's why once you act by G, they will fit together nicely and give you a smooth geometry. So this is the partition function here. Now, clearly, the idea is going to be inserting a complete set of states here to obtain the equation that we had. But let's understand, you know, what is the space of states then. Now, the Hilbert space of the theory on T3, of course, is going to be infinite dimensional. But in the supersymmetric case, we are doing a particular partial topological twist, which lets these answers to be independent of the length of this cigar. So in particular, this cigar can be stretched very long. And if you think of these states as being obtained by Euclidean time evolution along the radial direction of the cigar, then if you're taking this length to be very large, then essentially all the states get projected on the ground states. So in effect, one can assume the Hilbert space of the theory on the T3 for supersymmetric theories to be finite dimensional. Now, one can also try to think of these ideas in the non-supersymmetric context, in which this is not going to be true, and one would have to deal with all the infinitely many states that would propagate in this channel.
Sorry, Abhijit?
Yeah.
Is this pairing supposed to be positive definite? I mean, should I think about this cat as literally the bra if the G is trivial?
No. So this actually is a holomorphic type of gluing. It's not because of this partial, topological and anti-topological twist.
So it's not like the TT. Yeah, it's not like the TT star, but
it is kind of like that. But that's what makes it completely holomorphic and not real. It's not a real pairing, but a holomorphic pairing. This is something that was explained by Sarah and Chris and so on, Tudor first, I think, in the case of 3 dimensions.
Thanks.
Yeah, so I'm not gone into details of how that particular twisting works. But more generally, one can define, instead of defining just this partition function, one can define a partition function matrix where one has defects inserted at the core of the 2 solid tori. So I have an I type of defect inserted here and a J type of defect inserted here, which will alter the state appearing here and here, and it will let me compute the partition function matrix Zij, which is this one, with again a G label, of course, because the geometry we are considering Zg. So in effect, this would be the partition function on this geometry with 2 surface defect, one of I type and the other of J type, and they will intersect at a point. Now, in order to obtain, almost all the information about supersymmetric observables here, you simply need to take Ij vary over only n defects and not infinitely many defects. That's because n, I'm assuming n to be the dimension of this effective Hilbert space here. And as you change, if you take n different defects, generically it will span the entire supersymmetric Hilbert space that lives on T3. So in this talk, what we will do is choose a different basis, and not quite the surface operator basis, but a different basis for this Hilbert space. What we'll do is we'll pick an orthonormal state, set of states alpha on T3. Okay, so this state is sometimes also known as the vacuum of the Higgs vacuum of the massive theory on the solid T3. And now we define the states, which is the projection of this torus on this state alpha. Projection of the empty torus state on this state alpha. Okay, so this is how we are defining the state. So this is the coefficient involved in the projection, and this is the state itself. Now, in this basis, by construction, the partition function matrix is diagonal, because the orthogonality comes when you take inner product of alpha with beta on the torus. The coefficient that appears here,
maybe I missed this, but how do you argue that there's no zero modes? In other words, the Hilbert space is finite dimensional on T3?
So I don't know a general proof. I don't know general proof for in particular, the one knows of many non-Lagrangian theories, etc. Yeah. In that case, I don't quite know how the Hilbert space of the massive theory on T3 would look like. But in gauge theories, one can show that, simply by counting the vacua in the Higgs branch.
I see.
Massive theory, that there are finitely many.
Right.
But more generally, it would be nice to have some more understanding of the Higgs branch, if that means anything. Or more generally, just the effective Hilbert space on T3.
I see.
I guess you turn on holonomous for all the flavor symmetries and assume that vacua are isolated and massive or something like that.
Yes. So in gauge theories, yes, this is what you would do. Yeah. But more generally, I don't know if there is a way to argue for, or how to even understand this space for non-Lagrangian theories, say.
Also, has it ever, this analog of TT star in this setting, has it ever been explicitly worked out, like the deformation that leads to this property?
Well, in 3 dimensions, it has been worked out. And I think in 4 dimensions also people have worked on it.
Where? Because, like, I mean, the actual construction of Q-exact deformation that leads to this.
Yeah. Yeah, there have been some papers. I think Sarah was also involved in some, Wolfgar and so on. They have written on it, Wolfgar Pilas. Yeah.
Oh, I see CHIRAL posted some link, but is that, I thought it was something, okay. I thought it was something different,
Yeah.
but maybe what the Gayota, okay.
Yeah, maybe you can tell me what you have in mind later, maybe.
Mm-hmm.
Okay, so these wave functions, these are known as the holomorphic blocks. Okay, and the partition function that appears on the diagonal entries of this partition function matrix, they would have the interpretation of a partition function evaluated in a given Higgs vacuum. Okay, now from here we can derive this co-cycle condition quite easily. As I said, you just look at a particular partition function evaluated in particular Higgs vacuum as an inner product of the 2 Higgs vacua, like so, where you are having you take the bra to be evaluated on the geometry tau and the ket to be evaluated on this geometry, and then you insert a complete set of states and you normalize it appropriately, and finally you get an equation which looks like this. Now note that the things that appear here are not quite these partition functions in the Higgs vacuum, but rather normalized partition functions. So those normalized partition functions are the partition functions on the Higgs vacuum divided by partition functions on the Higgs vacuum with this particular geometry with gluing 1. So if you go back to this picture, if you insert the element 1 here, the identity element, the geometry that you would obtain is S2 times T2. So the denominator of this expression here is simply the S2 times T2 partition functions evaluated on this geometry. So this is what we are calling the normalized partition function. And it is the normalized partition function which has this nice co-cycle condition. So remember when I discussed this co-cycle condition, I said there is a caveat, and this is the caveat, that the partition functions that appear are these objects and not quite the physical partition function, these normalized partition function. Of course, you can go from one to the other if you know the partition function on S2 times T2. Now the co-cycle condition that
I have 2 questions about what you described until now. Can you hear me now, or?
Yes, I can.
First, in the 2D case, the picture was that you can think of the Hilbert spaces as states propagating along the 2 different cycles of the torus, and that's what gave you the S action. Or more generally, you pick a cycle, and then this is space, and then you propagate. Is there an analogous picture here, so that you take 2 different ways of thinking about the same manifold? And the second question, which is related to it, what's the physical interpretation of multiplying 2 different partition functions in the right-hand side of this equation?
Yeah, right. Yeah. So, good. Now for the first question, in 2 dimensions, indeed, you can think of the partition function evaluated in 2 ways. One, as something more states in the A side, on the A quantization, on the B circle. But I can think of it in the path integral point of view also, just as a partition function on T2, and the T2 has a large diffeomorphisms, and then things should be invariant under the large diffeomorphisms. So this is the point of view that I'm taking. This is, later on I will be discussing, how it fits in with the 2-dimensional picture and how it offers generalization in 6D and so on. So I will, maybe things will become clear then. But in this 4-dimensional case, the property is not quite coming from this type of understanding that you have 2 ways of quantizing things. So rather, you are it's coming from concatenating cylinders. So you have this particular geometry, G geometry, wherein you go from solid torus of parameter tau to solid torus with parameter G inverse tau, and then you can go from there to solid torus with parameter G2 inverse G1 inverse tau, or you can do this together, and these should be the same. Now, as it is, indeed, this is not giving constraint on the nose, because this is just relating the two partition functions, the partition function in the G1 geometry, G2 geometry, to the partition function on G1 times G2 geometry. Okay, things would have been clearer if this geometry were a cylinder, but they actually also work for when there is a ending of the geometry, when there is a tip. So in that sense, they're relating the two partition functions. And now physically, the picture for multiplying these two partition functions. So again, I'm not quite multiplying the partition functions. I'm multiplying partition functions evaluated in a particular state that is propagating in the middle. So it's kind of a block rather than a partition function. But in the supersymmetric case, they're just finitely, usually there are finitely many of such things, finitely many such things. They correspond to the Higgs vacuum. So yeah, I'm not sure whether I can say anything more right now. But later I will draw some pictures. I mean, there are some pictures in the slide and things will be slightly clearer. Maybe we can go back to this point later. Okay. Okay, fine. Now, the equation that I obtained from this reasoning seem to say that this partition function obeys this Poiseuille condition exactly, not with any phase that appears here. And that is because we assume that the states are given uniquely by these parameters. The states on the T3 are given uniquely by the parameters. Now, this will not be true if the way the space of states is fibered over this parameter space is curved. So if there is a non-trivial Berry connection, meaning a connection that has curvature, then if you are at a particular point in the parameter space, z, tau, sigma, and you change those parameters and come back to the same point, if the Berry connection is curved, you will not get to the same state, but rather with the state with the phase. And in doing what we just did, we are actually exploring a particular triangle of this parameter space, wherein we are going from tau to G1 tau, then G2 times G1 times tau, and then back to tau. So in that triangle, we could pick up a phase that is associated to the Berry curvature, and which is what will give us a phase to this condition that we derived. Now here I'm just making connection with something that is has been known. So this understanding of computing the partition functions by gluing together two parts of the geometries and thinking of it as inner product of two states is not new. This was done first in 3 dimensions by Sarah and Chris and Tudor, and then 4 dimensions also by Sarah. And then these holomorphic blocks also have been computed by localization somewhat more recently. Now, if you take that picture where you don't think about the Berry phase, then it will tell us that you can simply think of this partition function as a product of two inner products in this way, because this is just a diagonal entry. And the normalized partition function would be then simply the ratio of this block and the same block evaluated at a different point. Now, this is precisely the condition that will say that this z hat is cohomologically trivial, which is what will set the phases to 0. Okay, but as we will see that this is not true, that the z hat is not cohomologically trivial. So that is why what this equation is giving us is a local trivialization of this particular form, if you wish, and not quite global trivialization. And we will see this explicitly in the case of chiral multiplet. So before we do that, let's understand this SL3Z slightly better. So this is the picture that I had. Now I'm thinking of SL3Z as a 3. Yeah.
There is a question in the chat. For the n equal 1 or n equal 2 theories, has this Berry curvature been computed?
Well, the computation of the Berry curvature, I mean, one could do it directly in some way, but one way would be to evaluate the Chern-Simons phi form. That I will discuss that briefly, how to evaluate the Chern-Simons phi form, anomaly phi form, on a particular background to get these phases. It has not been done explicitly. It would be useful if it were done.
I see. And if you were able to compute it, would that restrict your phases even further? For now, it seems like there's just some generic phases.
Yeah, well, there are phases, but they are elements of the second group cohomology. So that already puts some constraints on these phases. So now, if there are other constraints, yes, I mean, then those would come from actually computing it from Chern-Simons anomaly form.
Okay.
Yeah.
Thank you.
By the way, Shlomo, how strict are we with the time? Cannot hear you.
You have about 10 minutes, maybe a little bit more.
Okay. Okay. So fine. So right. So I'm thinking of SL3Z as acting on this vector 1 sigma and tau. And usually the way SL3Z is presented is by defining the generators Tij, which have 1s along the diagonal and 1 on the ij entry, like so. And then one can think of SL3Z as being generated by Tij subject to some relations. But in order to make connections with the different SL2Z subgroups that act on these subspaces, the subspace of 1 sigma, sigma tau, and 1 tau, we will choose a different set of generators. We will choose Sij to be the S matrix that acts on the ij subspace. Then SL3Z, you can understand it as being generated by S23, meaning the S matrix acting here, S13, which is S matrix acting here, and T23, which is the standard T matrix acting in this space. Okay. This would be the SL3Z. If you want the Z cube, then you would have to include one element of the shift, which I picked to be T3, which is shift by tau. Now, this is important that there is a particular subgroup of SL3Z which is special, and this is the subgroup of those large transformations that not only are large transformations of the boundary but also extend into the bulk. Okay, which make them the large transformations of the full geometry, of the full half of the geometry, I mean, of the entire half geometry. And as a result, that makes the partition function or the wave function defined on those geometries to be equal to the wave function defined on the geometry with gauge parameter with gauge element 1. Okay, because you are simply doing the large transformations of the full geometry. This is more like the torus story of the 2 dimensions, wherein you are just demanding that the wave function should be invariant under large transformations acting on one side. Okay, so just to give you an example, if you were to consider a shift by tau, then that would keep the entire geometry invariant. So you would expect that to be an invariance of the wave function itself. But if you shift by sigma, which is of course a large transformations that is allowed for T3, but it's not a large gauge transformations of the full geometry, because if you shift Z by sigma, then that would need introduction of a flux, a unit of flux through this cigar. So that you cannot extend into the entire bulk. So that's why a shift by sigma is not going to be an element of this subgroup. So this subgroup is generated by these elements that I've written here. And it is SL2Z times Z squared squared. Now, as a consequence, the normalized partition function defined for all these elements or all these elements of this subgroup H should be 1 up to a phase. Okay, because they should be the same as identity gluing, because you are not doing anything effectively. So Now, going back, you saw that the SL3 is generated by S23, S13, T23, and this T3. And interestingly, almost all the things appear here, meaning normalized partition functions for all the generators are 1 except for S23. S23 does not appear here, meaning the only non-trivial partition function, normalized partition function, is ZS23, which is the element that gives you S1 times S3 geometry. So this is kind of nice that even though we have been working with partition functions with the G label, at the end of the day, the only independent or the only partition function that is to be constrained is only one, which is Z hat S23. Now, if you want the physical partition functions, as I said, you need to know the partition function on S2 times T2, which is Z1. Now let's get more concrete. In the chiral multiplet, you know Z1 and ZS23 from localization are given here, the theta function and elliptic gamma function. Now from here you can construct Z hat, which is the normalized partition function, by taking the ratio of this and shift this with a shifted argument. And once you have that, using the fact that all these Z hats of H are 1, you can construct partition functions for partition functions of the chiral multiplet on all the length spaces LPQ with any type of background flavor flux for the chiral multiplet. So here you can already see that how the first group cohomology constraint is letting you do that up to a phase, of course. Now, as I said, this cohomology, this first group condition is not just doesn't just let you fix the new partition, different partition functions from this single partition function, but rather it also constrains this partition function as well, the Z hat S23. So instead of this, we can, without loss of generality, take this independent element to be Z hat Y, where Y is the cyclic permutation. And then, as I said earlier, that it obeys this equation. Now the phase appears here, and this phase, this goes back to the previous question, how we can compute the phase. I will comment on that. But from chiral multiplets with R symmetry R or from gauge theories, you can see that this phase here is very closely related to the 't Hooft anomaly polynomial. In fact, you can see that it's exactly, almost exactly the 't Hooft anomaly polynomial.
Sorry,
then,
is it clear why there is this connection? Or is this just experimental observation?
Which connection?
The 't Hooft anomalies.
So the way you would compute this rigorously is by evaluating the Chern-Simons anomaly 3 form on a particular manifold. So that manifold would be a fibration of T3 on a disk, okay, where this fibration is going to be described by giving you group elements of how you go from it's going to be described by specifying how T3 fibers over the boundary of this. So T3 gets to another T3 with a G1 operation, then a G2 operation, and the G1, G2 operation goes back. And this gives you a non-trivial geometry in 5 dimensions, and on that you compute the Chern-Simons 5 form. Now I have not computed this explicitly, but because the thing to compute is the anomaly Chern-Simons 3 form, it's not totally surprising that in this most symmetric case, the thing that appears is the 't Hooft anomaly polynomial itself. In the various examples, it is the case. So for now, this is just a conjecture. It would be nice to compute this exactly by the Chern-Simons theory. Classical action of Chern-Simons theory. Okay. Maybe I'll skip this. Now for supersymmetric gauge theories, so for the chiral multiplet, it was quite simple because the alpha index took only one value. There was only one Higgs branch vacuum. So that's why all these constraints that were to apply for partition function evaluated in a given Higgs vacuum applied directly to the partition function itself. But for gauge theories, you have typically finitely many Higgs vacua. Those are indexed by this letter alpha. And the summand involves a perturbative part and a vortex part. The perturbative part consists of elliptic gamma functions, and the vortex part effectively is the contribution coming from vortices localized at the core of the solid T3. And this is usually, this appears as a bunch of theta functions, the ratios of theta functions. Now you can show that in cohomology, this z hat y is actually precisely this perturbative part. And because this perturbative part is just a bunch of elliptic gamma function, product of elliptic gamma function, you can explicitly check that this equation that I had is obeyed with P taken to be the 't Hooft anomaly polynomial. Now, of course, it would be more interesting to, it would be interesting to ask this question from a bottom-up point of view, wherein you specify the anomaly polynomial and ask question about classifying the space of gauge theories, meaning space of these partition functions, this obey this relation. Okay, so now let me move to some application. So, in 2 dimensions, of course, the great lesson from the modular property was the Cardi formula. So can we do something similar here? Now that we have a property that a partition function should obey, can we get to understand the high energy behavior of the operators? Now, indeed you can. So this is the constraint that the perturbative part of the partition function must obey. Now in the high temperature limit, now this is some fake supersymmetric high temperature limit. It is defined to be the limit in which sigma and tau go to 0 from the positive imaginary direction. In that limit, these two pieces, they go to 1. So simply the high temperature behavior of the partition functions get directly related to this 't Hooft anomaly polynomial. And you can also argue that the vortex part, which is missing from this equation, is subleading in the high temperature limit. And indeed, you get the high temperature limit to be described by this particular part of the 't Hooft polynomial. And the combination that appears here is 3c minus 2a. And this is exactly the supersymmetric Cardi formula that was derived in the context of gauge theories by directly working with elliptic gamma functions by Kim et al. And Kabowitz. Now here, let me mention the relation of this picture to geometry and how this can be generalized. So here perhaps things will get clarified. So in 2 dimensions, the modular property, you can think of it in the following way. So the 2-dimensional partition function is on T2. But instead of thinking of it as T2, let me consider that partition function to be on T2 fibered over a point. Okay. So one describes that the vibration is of a torus of tau, z and tau parameters. And this G labeled for this point describes that this torus has a different parameter, which is shifted by G. Now these two configurations can be interpolated by a 3-manifold, a 3-cylinder, that a mapping cylinder that I discussed earlier in the talk. So what I have done here is I have gotten rid of the fiber from this picture completely. So you should think of this picture with an extra T2 vibration. So you have a T2 vibration here, a T2 vibration here, and a T2 vibration here, and this T2 goes over another T2 with a G action like so. So then the modular property here is these two partition functions are almost the same except for the phase that comes from evaluating anomaly Chern-Simons form on this 3-manifold. Similarly, in the 4-dimensional case, it's one higher categorically speaking in some sense, wherein the partition function itself is now defined on a vibration of T3 on a line. So here the partition function was defined on a vibration which was on point, but here the partition function is defined on a vibration on an interval. Okay, this is the kind of geometry that we had here. And now if you want to go from the vibration from 1 to G1, G2 in 2 steps, by first going to G1 and then going to G1, G2, you should get the same result, except for the issues having to do with the Berry phase. As I said earlier, And that is obtained by constructing the geometry whose boundaries are this geometry and this geometry. As you can see, one boundary is this, and the other boundary is precisely this. And this gives you a phi manifold on which you should evaluate the 5D Chern-Simons anomaly form. And that should give you the e to the I phi G1, G2. So the conjecture was that when this G1 is taken to be Y, which was the most symmetric element, which obeyed Y cube equals 1, then this is Y, 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 and this particular geometry, if you evaluate the anomaly Chern-Simons phi form, then it should give you precisely the anomaly polynomial, with the variables being, tau, that appear in this vector tau. So it had a bunch of variables for the global symmetry, global holonomies for the background holonomies for the global symmetries, and they should appear as cubic polynomials of those variables. So this is not explicitly done. It would be nice to do this explicitly. Now this lets us conjecture a property for the 6-dimensional partition functions. So in 6 dimensions, we look at T4 fibrations on a disk. So learning from here, we go again one higher level categorically. So we have T4 fibrations on a disk. This particular diagram describes it completely. So here on this disk, on the boundary, T4 goes from 1 to G1 transform and G1, G2 transform and back to 1. Okay, so this is a disk vibration of T4 on a disk. And you can break this vibration up in this way and understand this as 3 fibrations glued in this particular way. And the partition function on these 2 manifolds should be the same, except for a phase that would come from a 7 manifold, which would interpolate between the 2 geometries. And then you would evaluate an anomaly Chern-Simons 7 form on this to give you this phase. In fact, this deserves more work. But a quick observation is that the simplest theory in 6 dimensions, namely the free chiral multiplet, its index is the double elliptic gamma function, and that indeed obeys an equation of this type, which looks like the modular property of the double elliptic gamma function of the SL4Z type modular property of the double elliptic gamma function. So this suggests that in 6 dimensions also the partition function should obey this type of a modular property. So now this is the last slide where I'm going to end with outlook. So most of the points here I've already made. So here I'm just saying that it would be nice to compute these phases explicitly from 5D Chern-Simons theory. Currently it is at the level of a conjecture, which is satisfied by gauge theories. Now this is also a point that I made earlier. It relies on understanding the Hilbert space of the supersymmetric theory on T3. We do understand it for gauge theories, which is the massive Higgs vacuum, but what is it for non-Lagrangian theories? It would be nice to understand that. And then this would let us apply all the results such as Cardi formula to non-Lagrangian theories. Now, the ideas go through, broadly speaking, for the non-supersymmetric theories as well. The main issue here in making these ideas concrete is that the Hilbert space on T3 is going to be infinite dimensional. We cannot project onto some finite dimensional subspace. So in that case, in order to see such a modular property for non-supersymmetric theories, one would have to consider a partition function which has only one state running in the T3 channel among, in an orthonormal, which forms a state of the orthonormal basis. And for that particular state, you would have an object which obeys this property. And even for free theory, I think it would be nice to do. And now, just from the geometric understanding, it leads to a host of conjectures. It would be nice to investigate them. In particular, I'm not even sure whether it's understood the way Natty and friends understood how to preserve supersymmetry on these line spaces, etc. I'm not even sure whether it's understood for, let's say, T2 vibrations on D2 in 4 dimensions or T5 vibrations in interval. But nevertheless, in either case, you have a set of conjectures which naturally follow from this geometrical understanding. and the connection to group cohomology, which is that in the T2 fibration W2, it should be the partition function should be element of H2 of SL2Z times Z squared to the power R, and for T5 fibration interval, it should be the first group cohomology of SL5, symmetric product of the Z5 to the power R. So they certainly deserve more investigation. Thank you.
Thank you very much, Abhijit. So let's thank Abhijit in various ways. Okay. Any questions?
Hi, Abhijit. May I ask a question, please?
Yes,
this
please.
is about non-superconformal R symmetry. Suppose that I have superconformal field theory which have, say, non-integer R symmetry. How do this property will know about such a superconformal field theory?
Yeah. Okay. Good. So. I guess what you mean by non-integer R symmetry, you had in mind superconformal R symmetry, right?
That's right, yes.
Yeah, so I'm assuming that there exists a choice of global symmetry charges, which when you add to the superconformal R symmetry will make the R symmetry integer. And if that is so, then I will just work with that R symmetry. Okay, and with that R symmetry, these results would go through. Now, the property of these partition functions is that they are invariant under RG flow. So even if you are working with a R symmetry that is not manifestly superconformal R symmetry, the observables that you will compute would be invariant under RG flow, and the results would hold for the superconformal theory that you find in the IR with these funny charges, funny R charges. And now, once you have those results, you can go back to the superconformal R symmetry. That final step may not be so straightforward, but for the Cardy formula, because the C and the A that appear here, using superconformal R symmetry is important, and for that you can go back and argue that that indeed, in terms of superconformal R symmetry, the partition function must obey this formula.
Okay, so assumption is that always exists, right? That choice.
Yes. Yes.
Okay. Thank you.
There is a question by Sharia. Please go ahead.
Thank you. It's maybe a naive question, but I'm just trying to understand your partition functions in 4D as automorphic forms for SL3Z semi-direct product Z2 to some power. So for example, in the 2D case, when they turn out to be Jacobi forms, you gave us a very nice formula, which basically showed us how the function would transform. And there was this one important thing called the index, which also turned out to be the central charge for your theory. So for these SL3Z semi-direct product modular forms, can you write down a similar formula?
Yeah.
So function in how many variables and how would it transform, and what is the analog of index?
Okay. So I argued that the four-dimensional partition function should transform in this way. So we had in 2 dimensions the equation which was z of tau should be equal to z of g inverse tau times some phase, and that phase can be characterized by the C, which was the index of this Jacobi form. Now in this case, even though this equation seems to be characterized by all these phases, at the end of the day, it should just be characterized by a few numbers, just like the index. These are the numbers which are the anomalies of the theory.
So are these numbers equal to R? R was the power of Z to the 2 in your you were considering?
No.
So how many?
So the R is simply the number of variables that appear here.
Yeah, that's what. Okay.
No, these numbers are the coefficients of the polynomial that appear. So if you remember, in 2 dimensions, C was a coefficient of this Z squared, right? Roughly Z squared over tau. So similarly, here also you would have this e to the I5s, and they would be functions of these, and the coefficients that appear in these polynomials would be those would be analogous to the index.
I see.
Now, unlike in 2D, there are many such equations, right? But all these phases come simply from a single anomaly polynomial. So only a few numbers appear over and over again in all these equations. So if you want some more mathematical understanding of this, there is a nice paper by Felder and Warchenko where they explicitly argue for this being automorphic form of degree 1 of SL3Z times CQ for the chiral multiplet. I mean, they don't have this language, but they want to talk about just the elliptic gamma function, which we know to be the index of the chiral multiplet with R check 0.
I see.
So they understand that with some rigor.
Okay, so they are, I mean, what is the homogeneous space here? So for example, for the Jacobi forms, it was upper half plane cross C.
Yeah. Upper half plane cross C meaning the Z, for the Z?
Yeah, for Z.
Yeah, okay. Right. Yeah,
I mean, because the quotient by this gives you the modular curve fibered by elliptic curves.
Yeah, right. So in this case, also the tau and sigma, well, okay, I've not thought deeply about whether they should live in the upper half plane and so on.
The analog of C is clear. That has to be R3. Because, oh no, sorry. I think that's still C because your semi-direct product is with Z2.
No, all these variables are complex variables. So in the two-dimensional case also, the C was the Z variable thought of as a complex variable, right?
Right.
Tau is the complex variable that lives in the upper half plane, right?
Exactly.
So in this case, the tau is replaced by tau and sigma.
Okay, so it's okay, so it's a complex two-dimensional space. That's
complex two-dimensional space, and then in addition there will be these Z-like variables, the Z-like variables. Now depending on the amount of supersymmetry. So in 2 dimensions, that particular discussion was in the context of 2, 2 supersymmetry. If you had less supersymmetry, then that Z would be replaced by a bunch more variables. In fact, even for 2, 2, you will have more variables. But usually in the literature, it's just a single variable that is discussed. So you would have more variables. So here also is the same exact case.
I see. Okay. I mean, there's still some. Maybe I can ask that. But so I had a question about the holomorphic blocks as well. So in 2D, there seem to be the analog of conformal blocks, and so in this case, is the I mean, they're finite dimensional.
Yeah, these holomorphic blocks, at least in the case of supersymmetric gauge theories, they are finitely many.
They're,
so the partition function is expressed as sum over these finitely many terms, each of which can be thought of as blocks, if you wish.
With this,
yeah, I mean, if you want to use the language of holomorphic blocks, they are kind of gluing of the 2 holomorphic blocks.
Right. So I can think of it as a vector bundle over this space.
Yeah.
In the tau parameter.
Yeah. Since we go over the time by a lot, let's just continue informally. But let's thank Abhijit for the great talk.
Thank you. Thank you.
Let's continue. Thank you. Okay, so there is a question by Ali and then Mikola. So Ali, please go ahead.
So I wanted to ask about the requirement of even integer R charges. Is that the requirement?
Yeah.
Is it even integer or just integer?
It is even integer if you want to work with all the length spaces, LPQ. So this is something that appears in Nati's papers. So I think the requirement is that if you want to preserve supersymmetry on LPQ, then the R charges should be multiple of 2 over P. So if you assume them to be even integers, then this would hold for all PQs.
Okay, I see. And you said that it doesn't have to be the R symmetry that we originally start with. It can be any mixing. It can be any U1, which you obtain as a linear combination of these different U1s. But then you also had a topological twist appearing in the story. So could you use that the mixing of U1 with the space-time U1 rotation symmetry and ask for the R charges under that to be even integers?
Well, so first point, let me address. So indeed, the superconformal R symmetry could be anything, but in this discussion, we never quite use the superconformal symmetry. We only use supersymmetry. So that's why you need not work with superconformal R symmetry, but you could add to it a linear combination of global symmetries, which would make this superconformal R symmetry an integral, an R symmetry with integer charges. And if that is possible, so this was the first assumption that I started with. So that I assume that this is possible, that there exists a choice of global symmetries, which would make the R symmetry have even integer charges. Now with that R symmetry, you could do the topological twist.
Okay, but the global symmetry that you started with has to be a flavor symmetry and not a space-time symmetry.
Yeah.
Yeah, okay. I see. Thank you.
Thank you.
Okay. Mikola, please go ahead.
So in this SL3Z has a subgroup SL2Z, which seems quite interesting from the point of view of chiral algebras in n=2 case. And then there's an expectation that this modular transformation should produce some kind of surface defects. Like, for example, for gauge theories, your Schur index has a form of matrix integral, which is like a over the middle dimensional cycle in the complexified maximal torus of the gauge group. And then as you do modular transformation, it gives you, it changes the contour of integration, which is also often expected as an effect of some surface defects. So have you thought that whether you can combine these ideas to maybe say something about how it produces surface defects upon modular transformation?
Well, okay, I should first say that this is Shlomo's work, right, on Schur index, the modular properties of the Schur index, the transformation of the Schur index. And I think that this SL3Z property should be related to it in the Schur limit. So if you take this discussion, apply to n=2 theory and take the Schur limit, then triviality of one side of the holomorphic block, one should be able to reduce this SL3Z property to the SL2Z property of the Schur index, although I have not done that explicitly.
Yeah, if you take the elliptic gamma function, then take the Schur limit, it just becomes a theta function, 1/θ function.
Yes.
And then the SL3Z just becomes the SL2Z.
You do have that. You do have this discussion. Yeah, right. But more generally, this is true for gauge theories also.
No, as Mikola said, then when you have gauge theories, you need to change the cycles. You act on trivially on the cycles, and then it's
no, but here also it's not quite straightforward, right? I mean, maybe if you think about a particular Higgs vacuum, etc., then this property may reduce to a SL2Z property. Yeah, I'm not sure, Mikola. Yeah, it would be nice to make the connection. I don't know.
Okay. Thank you.
I have a related question.
Yeah.
So again, in this 40-2 context, for the the SL2Z properties, is there supposed to be still a non-trivial barrier connection?
Yeah. I mean, because the index doesn't quite, the Schur index, the modular properties that the Schur index enjoys, it doesn't quite does have this phase in front of it, right?
Right. Then maybe for that case, one can extract this barrier phase even for the non-Lagrangian theories, just using knowledge of the chiral algebra. Yeah, I mean,
right. Yeah, I agree for non-Lagrangian theories also. I mean, extracting the phase itself for non-Lagrangian theories is not difficult, because at the end of the day,
we know the anomalies
will boil down to Chern-Simons. Yeah, but I think what is more interesting is to understand this Hilbert space on T3 with the mass deformations, meaning the background holonomics turn down, etc.
Yes.
For gauge theories, we know it's some Higgs vacuum where the global symmetry is broken in a certain way and so on. But but yeah, for non-Lagrangian theories, I mean, perhaps one could formally, at the formal level, one can derive some expressions using, let's say, a Lagrangian description, so-called Lagrangian description of the non-Lagrangian theories, or...
Well, I had in mind this this Higgs branch description that Leonardo in France has been proposing for, for chiral algebras. There's a like almost free field description using the beta gamma and stuff, using the chiral algebra.
Right, I see. Yeah, I think it's interesting. Yeah, I don't know. Yeah, maybe one can do that. Yeah, I had not thought about it from that point of view. I was thinking more formally, just as from the index. But yeah.
Yes. Thanks.
Okay. So thanks, Abhijit. In 3 minutes, we will start the gong show. So you're welcome to stay. So you were the warm-up band for the gong show.